Good afternoon. My name is Paolo Narvaez. I'm a principal engineer at Intel. I work in a different part of Intel than most of you are probably familiar with. There is a very large health and life sciences sector working on a number of very interesting projects in personalized medicine. What we provide in here is essentially expertise in big data and in computational performance. And we're trying to enable a new ecosystem that's revolutionizing the way medicine is being done in the world. I'm going to give you a very brief overview of what we do. I only have 20 minutes. Feel free to contact me afterwards for any follow-up or discussions. I hope this gives you a little bit of a break from other types of presentations and something, you might hear something new here. So let me just start with some basics, a little bit of history here. This is something I just took out of Wikipedia. Everybody knows this. This is a simple curve showing Moore's law. Spectacular the way that processors have progressed since the early 70s. So you can see 40 years worth of processor design have been following a very, very accurate exponential growth here, right? This is a logarithmic chart. And we do see that the so-called Moore's law really is working. Even people have been predicting the demise of Moore's law for many years, and we still have Moore's law working for us. This is a great thing. And this really has set up the expectation of what a CPU can do and what machines can do. People expect every 18 months you're going to have something exponentially faster happening. For much of the initial days of the CPU design, this really was everything you cared for. Every time you would have a new generation coming out, this generation will be automatically 50% faster, 100% faster in speed. There was very little that software engineers or application users needed to know about compute. You automatically got the speed up. The hardware engineers in companies like Intel build a faster processor. The software guys used it, period. However, sometime around the year 2000, people started predicting there was going to be some kind of tectonic shift going on. The reason for that is, yes, Moore's law is true. Moore's law still works. You can put twice as many transistors in a chip every 18 months, which is great. And you can use that to make things faster, which is great. However, as you make things faster, you make things hotter. If you kept the progression that was going on from the 386 all the way to Pentium 4, and by the way, this is a graph from the year 2000 when people started looking at this problem. Today we are about 0.015, so we're somewhere over here. We would have hit the sun's surface temperature a while ago. So clearly that's when people realize we can't just make things faster by taking advantage of Moore's law. If you're a computer company or a computational company, you cannot just run things faster. You really have to look in a different dimension. The person who wrote this graph used to be an Intel fellow. Pollack's rule was basically saying that yes, you can use this additional area that's in the die because your transistor count keeps growing and growing, but the increase in performance is only about a square root of your complexity. So if all you care about is single thread performance, your improvement is going to eventually not scale. And so this is when people realize that really power consumption or heat is really what's limiting single thread performance. We have to go to different type of paradigm. And this is what happened. So as you can see, going all the way down to the early 1970s, you had pretty much the same thing going on, right? And the whole world revolved around this very simple paradigm, which was just you write software to run a single thread. The computers get faster and faster, and you don't never have to worry about software again. And you have a very simple division between software and hardware. And in 2005, well, in 2000 is when people started realizing this wasn't going to scale. In 2005 is when it really didn't scale anymore. And you can see it very clearly here. The frequency is no longer going up. When you buy a new CPU today, if you buy a new CPU, you're not expecting your new CPU to be 4 gigahertz or 8 gigahertz or 10 gigahertz. We pretty much stopped at 3 gigahertz or 4 gigahertz. It's not going to go beyond that. And if you look at performance on a single thread, it's also leveled off. What has changed is the introduction of parallelism. Parallelism and also specialization. And this is where you see number of cores going up. That's one form of parallelism. But you also see that in terms of what's inside the CPU, which is a lot more complexity. You see that in terms of parallelism with SIMD, which is a vectorization form of parallelism, and new instruction sets. So the processors are becoming more and more complicated. But if you ran the same program that you wrote 20 years ago, today, you probably would have seen pretty much no benefit over the last 10 years, or maybe 5 years. So what does this, what does this mean? It means that in order to get benefits of this new paradigm, you really have to have the entire ecosystem understand two concepts, parallelization and specialization. Parallelization means that I can run things on many cores or many compute engines so that I can scale by having my processing done in many places as opposed to doing all the processing in one place at a very high speed. Specialization means that I can run my computation on the type of hardware that is most efficient. This means that if I have an accelerator, I can use that accelerator. If I have some custom hardware that addresses a specific type of compute problem or specific kernel, I can use that. Because our chips are getting bigger and bigger and bigger, and everybody else's chips as well, there is plenty of real estate in the chip to put as many accelerators or special type of compute engines as you need. So the key really is, in going forward, is how do we work with the rest of the ecosystem so that we take advantage of this. And I have just a couple of examples here. What's really in our hardware repertoires, multi-cores is a key thing. Vector units is huge. It's amazing what our new processors can do in terms of vector instructions. And this means you can essentially pack lots and lots and lots of values, integers or floating points, in a vector and process them together. New specialized instructions, graphical processors, not just Intel's, but NVIDIA GPUs and so on. Heterogeneous computing is very important. Fixed logic accelerators, even FPGAs. And we've recently announced a new server product, for example, that has an FPGA embedded in your CPU that allows you to work in this type of model where you have not everything running in a single thread, but you can offload depending on the type of compute. What this means for the company as a whole is that this is a very complex ecosystem where we can't just design chips in the abstract. We really have to work with the different applications, and we really have to understand what are the workload demands. And this means that we have really worked very tightly over the last 5 or 10 years with the domain experts and software developers. So, and you'll see more and more of this, that we're not working on it in isolation, but we're working with scientists, with software developers, with industry to design together. All right, so how does this hit healthcare? Healthcare is also a fairly complex ecosystem. You have a lot of interacting parts. It's different than other verticals that we deal with, like oil and gas or financials, here you really have lots of moving parts. So, life sciences, the bioinformaticians, this is genomics, this is huge, and I'm going to talk about that today. But you really can't just do progress in one of these sectors without realizing, okay, there's also a payer that has to pay for that. They're going to have systems that understand this. There's also a provider that's going to have to use that information. The doctor needs to know what the genomic result is. If I have the infrastructure in place to sequence everybody in the world, but the doctor can't use that information, it's useless, right? So there's a whole set of IT infrastructure that has to be developed as well to be able to digest that. And of course, the patient also has to be connected to this. All right, so this is just a general slide, give you an idea of all the things that we're doing to tackle this problem. This is a general list of the types of issues that we find every day when we talk to customers and partners here. Performance, this idea that so much software just runs on a single thread and is underutilizing compute resources. Poor scalability of algorithms, predominant problem we're seeing. Being able to work with domain experts like bioinformaticians is an issue. And finally, databases is a huge deal. How to actually handle all the information, all the data in a way that is friendly to both compute and to the human being is a challenge. It gives you an idea of the number of partners we have here. We have projects with all these various institutions. Going from hospitals like Oregon Health Sciences University or the Mayo Clinic, all the way to appliance builders, Amazon Web Services, and so on. All right, so now let me get into some concrete examples. I'm going to stop talking in general terms, and I'm going to give you a specific example of a collaboration that we've done recently to speed up the way that genomics works. Genomics is a really interesting problem to us because we can see that not too far down the road, we're going to be facing a major big data problem here. This is just back of the envelope calculation. If a certain part of the population gets sequenced, if 100% of the newborns in this country got sequenced, we'd end up with something like 313 exabytes worth of data. Similarly, if every patient gets sequenced every 2 weeks, every cancer patient gets sequenced every 2 weeks, we'd end up with something like 500. Right? So these are really vast numbers. Nobody really knows how to store this in a database that is useful to the country as a whole. So in order for this to happen, and there's willingness to happen at many levels, things really have to change. All right. So here's my my concrete example. The Broad Institute is leading world institute for genomics. It's a consortium between MIT and Harvard. They were responsible for sequencing the first the first human genome in the Human Genome Project, and they're leading other efforts today like the 1,000 Genome Projects and such. They have they're responsible for much of the software and algorithms and methods that are responsible. How do you actually sequence a genome? And I'm not going to go through the details of this, but this is sort of the kind of a recipe book taken from their website. There's a sort of a phase where you're trying to get your all the pieces of a single person's genome together. You're combining multiple genomes from multiple people, and then you do some sort of analysis together called joint variant calling, in which you're trying to find out what are the differences, and then you're doing some analysis with those differences afterwards. There is a very important piece, the only thing I want to highlight here which is joint variant calling, which is the part where you take all this data and you're trying to find out what is different for each individual. So if I'm comparing my data to my DNA to the DNA of all of you, there is something in me that most of it is going to be exactly the same. 99.9% of my DNA will match yours exactly. but there will be that 0.01% that is different, and that really matters. And so it's really critical to be able to detect that with fair degree of confidence, and that's what this component is doing. So when we first started talking to Broad, this was taking about 100 hours, or even above that. If for high coverage, it was taking 200 hours to just do that one component. The whole thing would take several hundred hours. We did this in collaboration with another institution, the Oregon Health Sciences University, which is a hospital in the Portland area, where much of my team is located. The first thing we realized is that the way that the pipeline was being run is extremely inefficient. Was taking a lot of hours. We spent some time to optimize this, introducing things like algorithmic improvements, thread level parallelism, cluster level parallelism, bringing it down to 44 hours. Beyond that, we realized that we really have to go into the details of the software and work with Broad, and that's what we did. We chose that one component that I mentioned before. Let me take that back a little bit. So one of the things we noticed is when we started profiling various data, and by the way, there is a tool that we released open source right now to be able to do this kind of analysis on how, not just genomic workflows, but pretty much any medical workflow performs on hardware. We wrote a tool to do these types of graphs and this type of analysis, and it's released open source. It's called Workflow Profiler. And what we've noticed is that, as you can see over here, the lines, this is CPU utilization. Most of the time, most of the cores are not even used, right? There are huge spaces here where we're not using CPUs. Likewise, I can show you with memory. Modern servers have hundreds of gigabytes of RAM, right? And many of these workloads are hardly using any memory except maybe during some peak times. So there's a lot of room for improvement. There's a lot of room to write software that actually uses the features that are in the hardware that, for the most part, in all the sort of bioinformatics fields that we're serving, are not being used. All right, so let me get back to the variant calling problem. We profiled that workload that was taking 100 hours, and we realized that the heart of the whole problem was this kernel. So this is a very complicated piece of software, had tens of thousands of lines of code, part of a bigger program that had hundreds of thousands of lines of code, but 70% of the runtime was just these lines of code. They were written in Java. They weren't taking advantage of data locality or any of the features. So we decoded what this was trying to do. We figured out this is trying to do a hidden Markov model calculation. We figured out what the dependencies were, and I'm not going to go through the details of it, but it was fairly elegant in that we first compute one value in this matrix, and then we have a dependency here where there are other two cells in this matrix that depend on that first value. And then there are three other cells that depend on those two values, and so on. And there's a progression. When you run this, the way this was being run is that each cell was being calculated independently. So first you calculate one cell, then you go to the next cell, then you go to the next cell. Each cell takes a certain number of steps. What we did is that we rewrote those few lines of code in a vectorized manner. That means is that instead of treating each cell as my variable, I treat each anti-diagonal as a variable. That's called a vector. So I can do this calculation one chunk at a time. So for example, in terms of calculating those values over there, I can calculate it in 5 steps instead of doing it in, what would that be, 5, 4, 9, 12, 14 steps. As you can see, as this gets wider and wider, it saves me a huge amount of time. That was actually a fairly easy fix, but had huge impact. It meant that instead of taking 100 hours to do this computation, it was taking only 30 hours. So huge difference. The results were actually kind of spectacular. We got 970x speed up compared to the original version. So once you start using vectorization, the optimizations that you can do in C++ plus multi-core, we're actually able to prove that we can run 1,000 times faster than Java. And if you look at the downloads of GATK over time, the version that we improved actually became the most downloaded version ever of GATK, and GATK is this genomics pipeline. So it had a vast impact on industry. That's one specific example that I have. Now I'm just going to give a very brief overview of other things that we're doing. There are a vast number, many other types of software out there in the bioinformatics world. The left is more on genomics, and the right is more on molecular dynamics. We have teams that are working on all these codes and optimizing all of these. I don't know if you're familiar with any of these, but we've done some pretty good improvements in many of these cases. We also partner with a lot of companies and startups. We have a partnership with a company called ASD, where we also used AVX vectorization to get speed up. So we saw a 400% improvement in their operations. We also have a collaboration with Scripps, in which we saw also a 4x improvement, but for a different reason. This was about faster I/O using SSDs. Aspera is a company that does fast communication over network, which is actually very important. These data sets are huge, so FTP doesn't work. You have to use something faster than that. We've collaborated with them to do that. Sanger Institute is a very famous institute in the UK. We work with them in terms of storage. They're using a Lustre file system that we've built for them. Finally, in terms of appliances, this is actually a very key thing, is taking an Intel server and being able to customize it for life sciences applications is something we did with Dell. And with a very nice story, we were able to cut down the delay for, this was done with Dell in another institute in Arizona called TGen. And they were using this for kids that had cancer. And we were able to bring down the time to do the RNA-seq, which is a different type of sequencing, not DNA, but RNA, down from 7 days to under a day, which is kind of critical for some of these very acute patients. Likewise, we have a number of collaborations with a bunch of appliances to do this type of optimization work in life sciences. If any of you wants to build an appliance, you're welcome, and you get help from us. And that's it. That's all I have. I think, as I mentioned before, really our goal, and this is being also stated by the head of our organization in servers as well as our CEO, is that we want to make personalized medicine mainstream for 2020. We do have a URL on the top that gives some examples of the work we've done with industry. That's my email if you want to contact me.